Here in lecture 19b of Differential Equations in Linear Algebra, we're continuing with the heart of abstract vector space theory, but we think about examples as we go. I want to revisit some things from the last lecture, 18b, look at some examples of vectors in Euclidean space and whether they are bases for three-dimensional space or not, based on row operations. We'll use Mathematica to do the row operations for us, but emphasize the concepts. We'll review the unique representation theorem, coordinate vectors, and ultimately coordinate systems. But something new is this coordinate mappings, and we will make precise the dimension of a vector space. Let's move ahead to the examples. Again, these examples are from lecture 18b. Let's just put them all on the slide here right at once. We're wondering, well, except for the first example, we're wondering whether these four examples are bases of three-dimensional space or not. Okay? Let me give you the intuition first, and then we'll check with Mathematica's row operation capability. You can use your calculator as well. That's a collection of three vectors in three-dimensional space. If you pick the vectors randomly, like down here, another collection of three vectors in three-dimensional space, in all likelihood, they will form a basis of R3, three-dimensional space. They will be linearly independent and span R3. And that does happen down here because I essentially picked those components randomly, somewhat, okay? However, this one I didn't pick randomly. You can notice a very clear pattern to these vectors. And by chance, in a sense, I wasn't expecting this, these actually end up being not linearly independent. They are linearly dependent, as we will see. And they also don't span R3, so they're not a basis. But we need to check that with the technology. With this example, it's two vectors in R3. And they're not scalar multiples of each other. They are going to span a plane through the origin in R3. They will be linearly independent because they're not multiples. But because there's only two of them, they will span a plane. If they were linearly dependent, if they were constant multiples of each other, they would span a line through the origin, one-dimensional space. Here there's two of them, they span a plane. That means it's not a basis of R3, because it doesn't span all of R3. Here's a collection of four vectors in R3. When you've got more vectors than their dimension, or in other words, the dimension is smaller than the number of vectors, that can't be a basis. It will not be a linearly independent set. It will span in this case, though it's not a guarantee. But in this case, it will span. So maybe pause the video, write these things down. I'm going to go to the Mathematica now here in a second. You can use your calculator if you want. Here's the first example. If you row reduce this matrix, you get a row of all zeros. That's the reduced row echelon form of it. That's the thing that makes this matrix, its column vectors, not form a basis because we had a row of zeros. Why? Well, you can think of it either in terms of the null space or the column space. If you make an augmented matrix where the last column is a bunch of zeros, that means you're thinking about the corresponding homogeneous system, x plus 2y plus 3z equals 0, 4x plus 5y plus 6z equals 0, 7x plus 8y plus 9z equals 0. And you're wondering, does that just have the trivial solution or does it have some non-trivial solutions? And because it row reduces to this, which is essentially the same as this matrix, except you have a column of zeros, the column of zeros is not affected by the row operations. What you see here, if you think about it carefully, is there's got to be infinitely many vectors in the null space of the matrix because there's a free variable. You can imagine a dashed line here for an augmented matrix. This corresponds to x minus z equals 0, or x equals z. This corresponds to y plus 2z equals 0, or in other words, y equals negative 2z. Where z is a free variable, it can be anything, including non-zero numbers, and that's going to mean the null space is non-trivial. In fact, it'll be a line through the origin. It'll be one-dimensional. What about, so that means that the vectors, the column vectors here, are not linearly independent. They are linearly dependent. That's what that means, about the definition of linear independence and dependence. What about the column space? I claim that it's not all of R3. How would you know that? Well, if you pick sort of an arbitrary vector on the right-hand side, that was somewhat arbitrary, somewhat random there that I picked, in all likelihood, you'll get an inconsistent system. Because if you think of this as an augmented matrix, the last line is essentially saying 0 equals 1. A contradiction. 0 does not equal 1. The assumption of a solution led to a contradiction. So there, with this particular right-hand side here, there is no solution. Now, if I formed a linear combination of these 3 column vectors and put that over there, then there would be a solution. But if you pick something randomly over here, there's not a solution. What does this mean? This means that these 3 column vectors do not span all of our 3 because, for example, this vector is not in their span. I'm not going to take the time to talk about the other examples for sake of time, but I do have the other examples in here. You can experiment with these things and think about them in the same kind of way to get the answers to the other ones. By the way, this one was a 3 by 3 with random entries, and it does produce the identity matrix as its reduced row echelon form, which is what will typically happen for a 3 by 3 if you make the entries somewhat random. All right, back to the PowerPoint. Let's move on. Coordinate vectors and coordinate systems, that's our goal here that we're trying to understand. We need a theorem, though, to make sure that coordinate vectors are well defined. That's the purpose of this theorem is. Let B, which consists of vectors b1 through bn, be a basis for a vector space V. For each, then the conclusion is that for each vector x in the vector space V, there exists unique, just like in differential equations, existence and uniqueness, scalars c1 through cn, so that x is a linear combination of the b's with the c's as the weights, like that. Okay? Mentioned this before. One thing that makes this a 4-credit course instead of a 6-credit course, say, is because we skip a lot of proofs. We should really be going through this linear algebra content more slowly and proving more if it was going to be a full linear algebra portion of the class. But we're skipping a lot of proofs. I hope this makes somewhat sense. You think about low-dimensional examples. You think about maybe the vector space V being R2, and B1 and B2, we'll look at an example here shortly, are not parallel on the plane. They should define essentially a coordinate grid. Yeah, I'll show you this in a bit here. On the plane, skewed coordinate system perhaps. And each vector in the plane can be written as a unique linear combination of those 2 basis vectors. That should make intuitive sense. Definition of the coordinates of x, the coordinate vector. If we consider B, B1 through Bn to be an ordered basis, in other words, not just a set. Sets are just collections of things. If I reordered these elements of the set, it would still be the same set. But now if I say it's an ordered basis, I'm saying it's really more than a set. I'm saying B1 comes before B2, comes before B3, etc. Comes before Bn at the end. Not, again, that it's B1 is less than B2 or less than B3. That's not what I'm talking about. I'm just meaning I picked some order. I could have picked a different order. But I picked some fixed order. Then the weights, the c's from the theorem, are called the coordinates of x relative to the ordered basis B. And we write this notation. Put the x inside square brackets and put a subscript of the b to emphasize what the basis is. Realize x is an element of an abstract vector space. It could be a function space. X could be a function of t, say. Could be a polynomial. What's its coordinate vector as a vector in Rn? This is an element of Rn. You create a column vector with the c's as the components. It is an element of Rn. This is no accident. We want that to happen. Why? Talk about why here in a second. Well, in a nutshell, it's useful. It's not an accident. We wanted it to be Rn. Keep in mind that non-trivial vector spaces with more than just the 0 vector in them always have infinitely many bases. It's not just a single basis you can pick. There are infinitely many choices. So I could have picked different B's, or I could have reordered these, and I would have gotten different C's and a different coordinate vector. So the coordinate vector is always relative to the basis. It depends on the ordered basis that you choose. Here's a new slide that I didn't show in the last lecture B. Some other slides are old ones that come after this. The mapping that maps a vector in an abstract vector space, x is in V, to its coordinate vector in Rn defines a linear transformation. And we could call it T if we want. So if I do that, if I call it T, with domain V and codomain Rn, I could also write T of x is the coordinate vector of x. I could write this equation here. Turns out this is a linear transformation. What does that mean? It's called the coordinate mapping relative to the given ordered basis B of V. What does it mean to be a linear transformation? It means it's linear. It's operation preserving. Operation preserving. I could use the T notation, as I always have to this point for operation preserving. I could write down the equation. But because T of x equals this new notation in terms of the coordinate vector, I can also write this. The coordinate vector of alpha x plus beta y, where alpha, beta are arbitrary real numbers and x and y are arbitrary vectors in, oops, this is a typo, in V, this should be a V, equals alpha times the coordinate vector of x plus beta times the coordinate vector of y. Okay? This is like T of alpha x plus beta y. This is like alpha times T of x. This is like beta times T of y, and you're adding. Yeah, that's a typo. Oh, these should be bold-faced. Bold-faced. Pretend those are bold-faced. Should be bold-faced. This does define a function, a mapping, or map for short. And it is a linear transformation. I'm not going to take the time to verify it. It's probably a worthwhile exercise if you really want to understand this stuff for you to try to verify this. It's based on the unique representation theorem, the definition of what a coordinate vector is, based on the ordered basis. Turns out the coordinate mapping is also one-to-one. Why? Because a given linear combination will define a unique vector in V. Why would that mean it's one-to-one? Well, remember, one-to-one means distinct inputs get mapped to distinct outputs. Or said another way, if the output is the same, then the inputs must have been the same. If I've got two coordinate vectors that are the same as column vectors, you could call them C1, C2 through Cn equals D1, D2 through Dn. Then that's going to mean C1 equals D1, C2 equals D2, C3 equals D3, etc. And that's going to mean that the vector that you make from those weights, in both cases, looks like this, either with the C's or with the D's, and it's going to be the same vector, x. The linear combination will be the same. Okay? Coordinate mapping is also onto. Why? Because given any vector in Rn, we can form a linear combination. Give me something like this, C1 through Cn. What vector in V gets mapped to this? Well, just make that linear combination, and that, by definition, is the vector that gets mapped to this one under the coordinate mapping. So it's onto. Okay? It's almost too easy, because it makes you confused sometimes when things are too easy. Therefore, we say the coordinate mapping is an isomorphism. I have mentioned that word before. And that V is isomorphic to Rn. They have the same form, algebraically speaking, and that is a useful thing. And when that's the case, we also write, as I mentioned before, V isomorphic to Rn, where that thing is written sometimes. Not everybody writes that. Some people just write that, and some people write this kind of thing. Or maybe just this. It doesn't mean V is approximately Rn in the usual sense of approximation. It just means that it acts like Rn with respect to all its algebraic properties. That's what it really means. This was an old one from the last lecture. The goal of introducing the idea of coordinate vectors and coordinate systems And the coordinate mapping I could add is twofold. It helps us relate unfamiliar vector spaces to the familiar Rn. And secondly, it helps us define coordinate changes in Rn. Maybe V is Euclidean. Maybe V is Rn. But the basis I use is not the standard basis. There are good reasons to do that. It's our main goal in applying linear algebra to differential equations and difference equations. The biggie from the first couple lectures. They represent changes in coordinates, new coordinate systems, skewed, for example, or rotated, to facilitate calculations, to make the calculations easier, and understanding of linear systems, especially changes in coordinates defined by special vectors called eigenvectors. Very soon, eigenvectors are going to be a real big deal for us. Real big deal. Maybe 3-4 lectures or so. Here's an example. This example I actually changed from lecture 18b, though it's similar. Let B1, oops, typo. Let B1 be 2 times the standard unit vector in the horizontal direction, or 2 times I hat, 2, 0. And let B2 be 2, 3. So there's one change I made. In the last lecture I just called it E1, and this was a 1 instead of a 2. Find the coordinate vector of 4E2, 4J hat, which is this. That's another change I made before, which is J hat. Why did I make these changes from the last lecture? It just makes the picture nicer, easier to see, that I'm going to show you. Goal is to find the coordinate vector of x with respect to the ordered basis B1, comma B2 of R2. So what would that mean we have to do? It would mean we need to find the C1 and the C2. We need to solve this equation, x, which is 0, 4, equals C1 B1 plus C2 B2, which is C1 times 2, 0 plus C2 times 2, 3 for C1 and C2. Sorry if it's out of the range of the camera here. But hey, this is nothing. I mean, I could do it with row operations, but I want to show you something else that's kind of neat. This is nothing more than a matrix times a vector. This is the matrix 2, 0, 2, 3 times the unknown vector C1, C2. So I could use this matrix to solve the equation. I actually haven't talked about using matrices to solve equations before. It is on my blog at infinitiesreallybig.com. Visual Linear Algebra Online is the online textbook. I did talk about using inverse matrices in the reading to solve equations, but I actually forgot to talk about it back 5 lectures ago or whatever it was. We're trying to find C to make this true. A times C equals x, where x is a fixed vector, it's this vector here, 0, 4, and C is an unknown vector. What you can do is you can multiply both sides on the left by A inverse, assuming it exists. And because of the associative property, the A, the inverse, and the A cancel, so to speak. They become an identity matrix. Write it up here. You can write it like this. That's the 2 by 2 identity matrix, and this thing becomes C. In other words, C equals A inverse times x. Back when I was talking about inverse matrices 5-6 lectures ago, I was only thinking about it in terms of linear transformations, and this could be thought of in terms of linear transformations as well. Now, A is a 2 by 2 matrix. I also wanted to mention, and forgot to this point, that there's a special formula for finding inverse matrices of 2 by 2 matrices. By the way, on the screen here, the matrix is not called A, it's called P. That's a pretty standard thing to call it. This is P here. I could have called it A, but it's pretty standard to call it P. Trying to solve that equation for this unknown vector right here. Multiply both sides on the left by the inverse of P, which will exist because the determinant of P is non-zero. Fundamental fact about determinants. So C is P inverse times x, the inverse of this matrix, which I'm initially just writing like that, times x, 0, 4. Here's the formula to find the inverse of a 2 by 2 matrix, avoiding row operations. You take 1 over the determinant of the matrix. This thing is the determinant of P. Notice P is this. Its determinant is 2 times 3 minus 0 times 2. 6 minus 0 is 6. And then you swap the numbers on the main diagonal, the 2 and the 3, become a 3 and then a 2. And you put negative signs in front of the numbers in the off diagonal. 2 becomes a negative 2, 0 becomes a negative 0, which is of course 0, but if this were non-zero, like 5 or something, this would become negative 5. I can simplify a little bit. 1/6 times this matrix gives me 1/2, negative 1/3, 0, 1/3. And now do this multiplication. This is the answer. That is what this vector C is. And C is the coordinate vector of x with respect to the basis. This is C. That's C. C is, by definition, a coordinate vector, the coordinate vector of the original vector x with respect to the basis. Somehow x is both equal to this and equal to that, because it's in different coordinate systems, that's why. Here's 3 pictures to visualize this. So to visualize the vectors from the previous slide in rectangular coordinates, rectangular and skewed coordinates, and then just skewed coordinates. So here's the original picture in the ordinary kinds of coordinates. X-axis is horizontal, y-axis is vertical. We think about the standard basis. This vector right there, that would be E1 or I hat if you prefer. Unit vector pointing directly to the right. This one pointing directly upward is E2 or J hat. B1 was 2 times E1. B1 was 2E1, 2, 0. B2 has components in rectangular coordinates 2, 3. Really with respect to the standard basis. X, that's my 0, 4 vector in the standard basis. When you talk about a vector's ordinary coordinates, it really means with respect to the standard basis, E1, comma E2, or I hat, comma J hat. And I was trying to write X as a linear combination of B1 and B2. And the answer I got was negative 4/3, 4/3 for C1 and C2. This red vector right here is negative 4/3 times B1. It points in the opposite direction as B1, and it's 4/3 times as long. 1.33 approximately times as long. It's pointing essentially, its endpoint is actually about at negative 2 2/3. And this blue vector is 4/3 times B2. Remember, C1 was negative 4/3, C2 was positive 4/3. And you can see the red plus the blue gives you the purple. Isn't that nice? Red plus blue gives purple. X is negative 4/3 B1 plus 4/3 B2. Here's the same diagram, but messier, involving slanted coordinates, using B1 and B2 to define the slanted coordinates, skewed coordinates. Notice you've got a line that's blue through the origin and parallel to B2. That is essentially, say, the V-axis, if you will. And you got a line through the origin parallel to B1. That's essentially the U-axis, previously called it X. If I call the new coordinate axes U and V, as I did back in the first couple lectures. Notice the first slanted line to the right of the origin goes through the tip of B1, the head, and it's parallel to this axis, the V-axis. And if you keep going the same distance with more parallel lines, you've got your new kind of graph paper. You can go backwards this way as well. And then you also see some horizontal blue lines right here, and down here, and down there. Those correspond to the height of the tip of B2 right there. slanted, skewed coordinate system. Still got the purple as the sum of the red and the blue. I can get rid of the original coordinate system completely now. And you see also that once again, the red vector here is still negative 4/3 b1. It points in the opposite direction and it's 4/3 times longer. The blue vector is parallel to b2. It's 4/3 times b2. It's in the same direction, but 4/3 times as long. Still giving you x. And in the new coordinate system, you go negative 4/3 units, so to speak, to the left, and then positive 4/3 units upwards along the slanted direction to get to the head of x. Okay, that's illustrating why x is this linear combination in the skewed coordinate system. Next slide generalizes what we did for the two-dimensional example to n dimensions. It's called the change of coordinates matrix. Suppose you got an ordered basis for Rn. Notice there's n vectors in the basis. That's not an accident. Right? You probably could have guessed that. Let P sub B be the n by n matrix whose columns are the vectors in the ordered basis, in that order. First column is B1, second column is B2, etc. The last column, nth column, is Bn. And this will be an n by n matrix because those vectors are all n-dimensional. I'm implicitly assuming when I put these in the columns that I'm using the standard coordinate system. So this is, the coordinate vectors of B with respect to the standard coordinate system. PB is called the change of coordinates matrix. Change of coordinates matrix from B to the standard basis that I'm actually even giving a symbol for, cursive E for Rn. It's called a change of coordinates matrix. If we suppose that x is in Rn, and if the coordinate vector of x relative to the ordered basis B is that, notice I use the transpose again, so this really represents a column vector. It just didn't have enough space, so that's why I saved space by writing it as a row vector, but by putting the transpose operator, I'm really emphasizing you should think of it as a column vector. Then, x, in terms of standard coordinate system, the standard coordinate system is PB times the B coordinate vector of x. Why? Well, x, based on the basis, the ordered basis B, can be written uniquely as a linear combination like this, C1b1 plus C2b2, etc. That's the unique representation theorem. But hey, that's a linear combination of a bunch of column vectors. And hey, P is defined to have those vectors as its columns. And hey, this vector, this coordinate vector, is defined to have the C's as its components. That's the definition of a matrix times a vector. A linear combination of the columns of the matrix with the components of the vector as the weights, which is what you see. So by definition, this has to hold. Since B1 through Bn is a basis for Rn, there's something called the invertible matrix theorem, which I haven't talked about. I could have before this point, but I just haven't. That will imply that P is invertible. And you can solve this equation for the coordinate vector of x by left multiplication by the inverse of P. PB inverse. And that inverse matrix will exist by the invertible matrix theorem. And why can you conclude that? It turns out the reason you can conclude that, the reason you can use the invertible matrix theorem is because this is a basis. It's a linearly independent set of n vectors here that spans Rn. It's going to be an invertible matrix, and this equation holds the same thing I just wrote down in green. Okay? So the P matrix itself transforms the new coordinates back to the old coordinates. The new coordinate system to the old coordinate system. It's its inverse matrix that transforms the old coordinates to the new coordinates. So in general, you might have to solve for the inverse. If it's 2 by 2, you can use the shortcut formula that I mentioned 5-10 minutes ago. If it's 3 by 3 or 4 by 4, etc., you've got to use the algorithm for finding the inverse matrix, which can be a real pain. And even as n gets moderately big, 10, 11, 12, 13, computers start to bog down as well. There are better ways of computing this actually within that avoid inverse matrices, but I'm not getting into that right now. But in theory, it still should make sense, and you can still say it's true. All right, last slide. Dimension of a vector space. Actually, I'm not sure if it's the last slide or not. Just see here quick. Yes, it is. Okay. I've been hinting at dimension all along here, hinting at it. Coordinate vectors can help us define the dimension of an abstract vector space. They can be useful in proving this theorem, for example. That's one way coordinate vectors are useful. Another way coordinate vectors are useful is they can help you figure out, for example, if a given set of polynomials is linearly independent or not, for example. Or a given set of more general functions like cosine of t and sine of t and maybe some other trig functions are a linearly independent set or not. The theorem says let V be a vector space with basis B, and I'm not saying it's an ordered basis. It doesn't have to be ordered here. I could rearrange the order of the B's and it would still be the same set, the same basis. Then there's three things you can say here. Number one, any set in V with more than n vectors must be linearly dependent and therefore can't be a basis of V. Any set with fewer than n vectors cannot span V and therefore cannot be a basis for V. 3, every basis of V must have exactly n vectors. When it's got one basis with n vectors, every basis has to have n vectors. This is a theorem that can be proved, and you can use coordinate vectors to prove it. I hope it makes intuitive sense based on thinking about Rn. And even the example right from the beginning of this lecture. Examples. This leads to a definition. Let V be a vector space. If V is spanned by a finite set, then V is said to be finite dimensional. If there's some finite set that spans V, everything in V can be written as a linear combination of the things in the finite set. That's going to mean the basis of V is finite, and so V will be finite dimensional. This symbol, dim V, equals the number of vectors in any basis. Dimension of V equals the number of vectors in any basis. It's the theorem that makes this make sense. We also define the dimension of the trivial vector space to be the number 0. So that's a boldface 0 representing the trivial with the 0 vector. You could think of it as part of any vector space if you want. But all trivial vector spaces are isomorphic, so it's not a big deal. That's the number 0, it's not bold-faced. Finally, if V is not spanned by any finite set, then V is said to be infinite dimensional. And we could maybe write dim of V equals infinity. Well, you could, but it would just be notation. I will avoid it. What's an example of an infinite dimensional vector space? Well, one example is the function space consisting of all continuous functions defined in a closed interval and continuous on that entire interval, or the continuously differentiable ones, or even just the collection of all cosines and sines of different periods. Cos t, sine t, I mean the span of this. Cos 2t, sine 2t, cos 3t, sine 3t, etc. This is an infinite collection of functions The span of such a set, as I have mentioned before, is the set of all linear combinations that are finite linear combinations, because we don't want to worry about convergence. So even though this is an infinite set, the span is the set of all functions that are finite linear combinations of the functions in the set. That will be an infinite dimensional vector space as well. Any vector in there cannot, well, there's no finite, think of it this way, there's no finite subset of this that will span the space. That's the best way to think of it. Theorem, if H is a subspace of a finite dimensional vector space, V, then any linearly independent set in H can be made bigger, expanded to be a basis of H, if it's already linearly independent to begin with. May not span, so you may have to make it bigger. Furthermore, the dimension of H is less than or equal to the dimension of V. That better be true. If H equals V, then the dimensions will be the same. If H does not equal V, then actually you can put a strict less than there. If H does not equal V. And finally, we have ended with something called the basis theorem. Let V be an n-dimensional vector space with dimension greater than or equal to 1, so V is not the trivial vector space. Then, two things can be said. Any linearly independent set of exactly n vectors and elements is automatically a basis for the vector space. If it's linearly independent and it has n elements, n vectors, it will automatically span. On the other hand, any set of exactly n elements that spans V is also automatically a basis for V. If you know it's spanning set with exactly n elements, where n is the dimension of V, it will automatically be a basis. It will automatically be a linearly independent set. So again, we go through these things, we think about examples, we don't really focus on proofs. But I hope these things still make intuitive sense. Examples help, but you need to be able to think abstractly. Thinking about low dimensions, 2 and 3 dimensional examples can help, but again, you need to be able to translate that into abstract math. And we will shortly see it's useful for differential and difference equations. Thanks for watching.